In an economics book, 48% of the pages had some kind of data display, and 27% of the pages had an equation, and 7% had both an equation and a data display. What percent of the pages had neither a data display nor an equation? Well, first off, I look at this and I go, hey, you know what? I have two things and I have a both. When I see I have two things and a both, I honestly go straight to the general addition rule. So I'm going to write that down. Probability of A union B equals the probability of A plus the probability of B minus the probability of A and B. And once again, a lot of times you have to sit there and go, hey, what do I know? I don't necessarily know how I'm going to get there yet. I'm just going to have to trust that I know something. Let's start organizing. Well, I know I have both. Well, both is my intersection. So this is 0.07. And then we have 0.48 plus 0.27 minus the 0.07. Okay? When I add all that up, I get the probability of A union B equals 0.68. But that is 4. That's the probability that I have a data display or an equation or both. That's what that is. They didn't ask me that for that. They asked me for what's the probability I have neither. They asked me for the probability I have neither. And it's like, oh, this is the probability I have something, so I want not something. So I can go 1 minus 0.68 and equal 0.32. So this is the way I tend to think about this. Having said that, I'm going to look at this, and I've gotten a couple questions. Hey, could we have done a Venn diagram? Yes, you could have. I'm not going to do a Venn diagram because I don't draw them very well, but I'm going to show you the same thing with the table. And I'm just going to put this on the screen so you can see it because I've already done it. All right, with the table, I have equation, no equation, data display, no data display. I know I have 100% right here. Well, 48% have a data display, and 27% have an equation, and 7% have both. So 27 minus 7 gives me 20. All right, and so when I add all this stuff up, by the way, what did I do something wrong here? There is something horribly wrong with this. Excuse me for that. I'm going to have to fix that. I so apologize. So let's go ahead and make a new one because apparently I got typo crazy on it and didn't catch myself. So try this again. So we have data, no data, and a data display shows up. Data display shows up 48%, so 0.48. All right. An equation shows up 27%. 1 minus 0.27 is 0.73. Try that again. I apologize. There we go. And then 1 minus 0.48 is 0.52. Now, we know 7% of the time we have a data display and equation. So this is my intersection. So this becomes 0.20 because 27 minus the 7 is 20. 48 minus 7 is 41. And 41 minus 73 is 32, and this plus this equals 32. Well, guess what? Now I know some of you did Venn diagrams, and that's fantastic. I'm just not very good at drawing them. They asked for no data, no equation, no data display, and that's right there. So if you had wanted to use that, that would work, okay? All right, sorry about the mistake I made earlier on that. I don't know what I did in the way of typos, but anyway. So what is the probability that a randomly selected page in a book has a data display if it has an equation? All right, so going back to my table, we have what is the probability a randomly selected page in a book has a data display if it has a table. This is like saying, this if word is like saying given. So I have a given here, and anytime I have a given, I have an intersection. Well, what is the probability given it has an equation? Well, what percent had an equation? We know 27% had an equation. So this is 0.27. And we want the intersection with data display, which is 0.07. That's the intersection of data display and equation. So this is 0.07. And this equals about 0.2593. All right. A six-sided die is weighted. The number 1 occurs 30% of the time. The number 2 occurs 15% of the time. The number 3 occurs 20% of the time. The number 5 occurs 10%. And the number 6 occurs 5%. What percent of the time is the number 4 rolled? Well, in this case, and I'm just going to put this up here to try to speed things up a bit, 1 minus the sum of all the probabilities. When I do that, I get 0.8, and so my answer on this one, the probability of 0.4 of 4 is 0.20, or 20%. It should have been 1 minus 0.80 equals that 0.20. All right. Next thing, what is the expected value? You did not need to show me a table, but I'm going to put the table here because these are all the probabilities. And by the way I actually go about doing the work versus the way I show the work are two different things. Showing my work looks like this. My X value times its associated probability. My X value times its associated. So 1 times 0.3 plus 2 times 0.15 plus 3 times 0.12. This is the work that you show. What I actually did is I plugged this into the calculator and I ran it. All right, I actually just plugged it into the calculator and I ran it, putting this into L1 and L2. So this one into L1, this one into L2, and I did a stat edit, stat calc, and I ended up getting 2.8. Standard deviation. Well, I got the standard deviation when I plugged this in the calculator. But once again, I got to show my work. So the formula is my individual x's minus my average times the probability. My x of 1 minus my average of 2.8 times its associated probability. My x of 2 minus 2.8 times its associated probability. And notice, plus dot 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 plus. I even ran out of room on the paper typing it. So you can always do first and last. You can bookend it just like this. I included more just so that you could see it, but essentially this is, I bookended it, and you're welcome to do that too. And this ends up being my answer here. If the dice is rolled 7 times, what would be the expected value of the sum of the rolls? Well, essentially it's 2.8 plus 2.8 plus 2.8. And some of you are going, hey, Mr. Spencer, I'm smarter than that. I just went 7 times 2.8. And I'm going to go, you know what? You are smarter than that. This is good. This would absolutely be correct. There's no reason for you to sit there and do all that. But I just wanted to show you that that's where it came from. Okay, because this is actually, like I said, I get to the second or third one and I go, hey, I could just multiply, and there I'm good to go. The next thing, the standard deviation. So what I want to do is I want to go 1.5362 plus 1.5362. And I go, wait a second, I cannot add standard deviations. I have to square them. So I square them and take the square root of them. And that's what my work shown, okay? And when I do that, I ended up getting this value, unless I have a typo, which very well might, because we've seen several tonight. All right, last page. Still on the weighted die problem. And by the way, I'm just telling you, anytime you play a game twice, you need to make up the sample space. This one was very forgiving, but you really, really need to set up sample spaces, and I can tell you that it is going to occur on the test that you're going to need to set up some sample spaces. And like I said, the key thing is a game is played twice. If it's repeated, set up the sample space. So we're back to the six-sided die. It happens to be weighted, and it says creates a sample space for all winning combinations, and we win if the sum shown on the two faces is a 6. So my winners are 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. And before I take the test, if I were you, I would practice making this table, write it as fast as you can, about 4 times, and then I promise you, you won't take any time on the test doing it. You won't have a problem. So 1 plus 5 is 6, 2 plus 4 is 6, 3 plus 3 is 6, 4 plus 2 is 6, 5 plus 1 is 6. So my winning combinations are the 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. Question 18, what's the probability that a person will win? Well, these were my probabilities, 0.3, etc., and I just copied them from the previous page. You don't have to rewrite them, but I rewrote them just because I was trying to shorten things up so that you'd understand where I got them. All right, so I need a 1, 5, a 2, 4, a 3, 3, a 4, 2, or a 5, 1. Notice I put an or here. And I want you to think about this. I cannot roll a 1, 5 and a 2, 4 at the same time. It's either or. They're mutually exclusive. Because they're mutually exclusive or they're disjoint, we can add them. All right? So the probability of getting a 1 on the first die is 0.3. The probability of a 5 is 0.1. And I do this all the way across. For the 2, I get a 0.15. For the 4, I get a 0.2. For the 3, I get a 0.2. And the 3, I get the 0.2, etc. All the way across, I sum them up. And the probability that I get a sum equal to 6 and win the game is 0.16. So there's about a 16% chance of winning. Now, what that means is, on average, I would expect to win 16% of the time. I might play it 100 times and win 12. I might win 20. But on average, if we played it enough times, we expect to win 16% of the time on average. I've gotten a few people asking me, hey, if we circled these, is that good? For my test, yes. Matter of fact, I probably would have, if I'd been you guys, I would have probably done that and said, hey, winners. Okay? Those are my winners.